You know, language can be really tricky. We humans handle ambiguity without even thinking about it, but for a machine, figuring out context is a huge challenge.
Take a simple sentence like this one. How does a machine know that it refers to the ball? The answer isn't just about the words nearby. It's about understanding the relationships between all the words in the sentence, no matter how far apart they are.
This is the exact problem that a revolutionary architecture called the transformer was built to solve. And by the end of this explainer, you'll get exactly how it works, how it shifted AI from a slow, word-by-word process to seeing the whole picture at once.
Okay, so to really appreciate why the transformer was such a game changer, we first have to look at the problem it solved. And that problem was something called the sequential bottleneck.
Before transformers, the go-to models were things like recurrent neural networks, or RNNs, and they process text one word at a time. Seriously, imagine trying to read a long novel through a tiny keyhole. By the time you get to the final chapter, you've probably forgotten the details from the beginning. That was the core issue for RNNs. They were slow, and they really struggled to connect words that were far apart, losing crucial context along the way.
And then, in 2017, everything changed. A team at Google published a paper with a pretty bold title, "Attention is all you need." And it turns out they were onto something huge.
The core idea was brilliant in its simplicity. Instead of that one word at a time slog, the transformer looks at the entire sentence at once, all the words all at the same time. This was a massive deal. First, it meant you could use powerful GPUs to process everything in parallel, which made training way faster. And second, and this is the crucial part, it meant the model could directly compare every single word to every other word.
And the magic ingredient that makes this all possible? It's a mechanism called self-attention. Think of it as a system that allows the model, for any given word, to weigh the importance of all the other words in the sentence. It's how true context is built.
All right, so let's pop the hood and see what's actually inside a transformer.
At the highest level, you can just think of it as a black box. You put a sentence in one language in and get a translation out. Simple enough. But if we open that box, we find two main parts, an encoder and a decoder. And inside both of those, we find the real workhorses, that self-attention layer we just mentioned, and a standard feed-forward network.
So the encoder's only job is to read the input sentence. It takes all the words in at once, and using self-attention, it builds a rich numerical representation for each word that's packed with context from the entire sentence. It's not producing an output yet, it's just trying to deeply understand the input.
Once the encoder has a solid understanding, it hands that information over to the decoder. The decoder's job is to generate the output sentence. Now, interestingly, it does this one word at a time. To decide on the next word, it looks at the encoder's rich representation and all the words it has already generated. This process is called autoregression.
So that brings us back to the core mechanism, self-attention. How does it actually work? Well, the most intuitive way to get it is through three concepts: a query, a key, and a value. Here's a helpful analogy. For every single word in the sentence, the model creates three distinct vectors. The query is like the word asking a question. Who in this sentence is most relevant to my meaning? The key from every other word is like a label saying, here's the kind of information I have. The model compares the query from our word to the keys from all the other words to find the best matches.
And when a query finds a key that's a strong match, the model then takes that word's value vector. The value is what contains the actual substance, the meaning of that word. So, by blending the values of the most relevant words, the model creates an updated, context-rich representation of the original word.
So, at a high level, the process looks like this. First, you score the relevance between a word and all other words. Second, you normalize those scores into weights, basically deciding how much attention to pay each word. Third, you combine those attention weights with each word's value vector. And finally, you sum everything up to get your new, context-aware word representation.
Now, the model doesn't just do this once. A technique called multi-head attention runs this entire query key value process several times in parallel. You can think of each head as a specialist. One might focus on grammatical relationships, while another tracks who did what to whom. This gives the model a much richer, multifaceted understanding of the text. So this whole system of attention isn't just some clever idea. It is, without exaggeration, the foundation of nearly all modern large language models.
And after that 2017 paper, things moved incredibly fast. Just a year later, we got two landmark models, BERT from Google, which used just the encoder part, and the first GPT from OpenAI, which used just the decoder part. These two models really kicked off the generative AI explosion.
This basically gives us the three main flavors of transformers you see today. You've got encoder-only models like BERT, which are fantastic for understanding text. You have decoder-only models like the GPT family, which excel at generating text. And you have the full encoder-decoder models, which are perfect for tasks that transform input to output, like translation.
Today, this architecture is just everywhere. There are well over 50 significant models, all built on this same fundamental idea. It's become the absolute backbone of natural language processing and generative AI.
So, to wrap it all up in a single sentence, the transformer architecture processes entire data sequences at once using self-attention to build a deep contextual understanding.
If you remember just one thing, let it be this. The key takeaway is the shift from slow, sequential processing to fast, parallel attention. That fundamental change is what unlocked the ability to train the massive models that power so much of today's AI.
And this leaves us with a final thought. We've seen how attention has helped us master the complexity of language. What other complex systems, from biology to finance, are just waiting for a similar breakthrough?